Yeah. Is the screen visible? I had closed it in between. Hello?
Yes, sir, it is
Yeah.
visible.
Okay. Yes, sir.
Yes,
Yeah. Okay. Okay. So today I'm going to start with the nonlinear problems. So if you look at the nonlinearity, so where now we have the problem involving the stiffness matrix is dependent on the displacement vector. So that leads to nonlinear problems. And the nonlinearity could be of two types. One is the material nonlinearity. The other could be geometric nonlinearity. And material nonlinearity means what we are talking about is the nonlinear stress strain relation. So you have nonlinear stress strain relation. And in this we will talk about two type of problems. One is the elastoplasticity, and the other is the nonlinear elasticity. And specifically I will be talking about hyperelasticity. So under the material nonlinearity we are going to talk of two things: elastoplasticity and the nonlinear elasticity. In both, the stress strain relationship is nonlinear. And in the geometric nonlinearity, mainly what we are going to talk about is the nonlinear strain displacement relations. Nonlinear strain displacement relations. So if you look at the green Lagrange strain tensor, so there are quadratic terms. So if the displacement gradients are large, those quadratic terms are important. And if we consider those quadratic terms, then the problem becomes geometrically nonlinear problem. So no, under these categories, so in elastoplasticity there is a plastic deformation. So we are still assuming that strain displacement relations are, although no, in elastoplasticity you could have finite deformation, you can have infinitesimally small deformation. So we are going to consider infinitesimally small deformation. So we will, that is what we would consider. And then in the nonlinear elasticity we will consider finite deformation. So there would be geometric nonlinearity and also material nonlinearity. So that's what we would consider in hyperelasticity. And there can be purely geometric nonlinearity where only nonlinearity is in the strain displacement relations. So then you will have to model that accordingly. So let me start with the small deformation rate independent elastoplasticity. A small deformation means the displacement gradients are small, so the quadratic terms in the green Lagrange strain tensor are negligible, so only you have linear strain displacement relations. So a small deformation rate independent, so we are not going to consider the rate of deformation in this. So it is like no small rate of loading, so it is like quasi-static rate of loading. So a small deformation rate independent elastoplasticity. So now in this, see, if you would have learned that if you look at the uniaxial case, uniaxial stress strain curve. So if I have this as sigma xx and this as epsilon xx, and look at the stress strain curve, so typically you will have the initial linear elastic region and then the elastoplastic region. So this is the your starting yield point. So this is the yield stress, let us say the initial yield stress sigma y naught. And if you have loaded up to some point, and if you unload it, so the unloading would be the slope of these two. So let us say this is the slope E, this is also this slope will also be E. So this is loading path, and then this is the unloading path. So it would be like this. And now in this part of the strain, which is permanent strain, is the plastic strain. So epsilon xxp. And this part which is recovered, so this much is recovered, no, this part. So this part is epsilon xx elastic, and this is uniaxial stress strain curve. Uniaxial stress strain curve. So now you have the total strain. The total strain at this point is, let us say, epsilon xx. So that epsilon xx is gets divided into two parts, the epsilon xxp. So here epsilon xxp is plastic strain, that is permanent strain, plastic strain, and epsilon xxe is elastic strain. So now to yeah, but of course this is uniaxial stress strain curve. So when we do the material characterization, this is what we do. But ultimately this has to be extended to a multilinear problem. So you know, it has to be extended to triaxial state of stress, and so we have to know have the appropriate concepts for that. So we will be discussing that. So before that, now you will see that if your loading is within the elastic limit, so then it's a linear elasticity problem. But when you are going now in this range, so then you see that there's a nonlinear relationship between the stress and strain. So it's a nonlinear problem, and there is a permanent deformation in this. So first I'm going to talk about the principle of virtual work for a general case, general three-dimensional case. Let me develop the element level governing equations, and then I will be talking about the various concepts involved in elastoplasticity problems. So first I am going to talk about a principle of virtual work for a general 3D state of stress and strain. So I'm going to use the no write the stress tensor and strain tensor using void notation as vectors. So I'm using here, using void notation, we can write the principle of virtual work as the integration over volume, variation in the strain. So strain is 6 components, and similarly stress is having 6 components. So this is the virtual work of internal virtual work of stresses. This is the basically the you can say the virtual work of internal stresses, then minus the virtual work of externally applied forces. So there can be body forces and surface forces. So the body forces, the virtual work of body forces would be delta of UVW transpose into the body force per unit volume in the x direction, in the y direction, and in the z direction. So FBX is the body force along x direction, FBY along y, and FBZ along z. So this is dV, and then minus you have the virtual work of surface forces. So delta of UV transpose into, let us say, the surface traction is denoted by T, and the components are T and X, T and Y, and T and Z ds, and this is equal to 0. So this is the virtual work. So rather than starting from the no stress equations of equilibrium, I am starting directly with the principle of virtual work. One can actually start from the stress equations of equilibrium, write the first the Bettet residual statement, then weak form, and that weak form would be coming out to be the way I have just written this principle of virtual work. In the
Sir,
subsequent yeah.
sir, in the first
Yes.
term, there should be one epsilon also after sigma.
No, there's only one epsilon, delta epsilon transpose into sigma. So this is the virtual work of stresses sigma. There is no additional epsilon. When we write in terms of the constitutive relation, no, that sigma is written as constitutive matrix into epsilon, then
Yes, sir,
you get
understood.
sigma epsilon.
Yes, yes.
Then you get
Sigma
sigma epsilon.
into.
But here it will be sigma.
Yes, sir.
Yes. So this is I'm going to denote as body force vector FB, and this I'm going to denote as traction force vector T. So now here the delta epsilon will be defined these quantities. So delta of epsilon I am talking about is delta of epsilon xx, delta of epsilon yy, delta of epsilon zz.
There's some
And
noise
in this,
problem is coming.
hello, yeah, some I think somebody is unmuted. Please mute yourself. Unless no, you want to ask something or you want to talk, you should mute. So delta of epsilon is delta epsilon xx, delta epsilon yy, delta epsilon zz, and the engineering shear strength. So I am using engineering shear strength, or you can write twice of tensorial component of shear strength. So delta of gamma xy, delta of gamma yz, and delta of gamma zx. So this is what delta of epsilon in the notation I have used for the virtual work, and sigma is vector sigma xx, sigma yy, sigma zz, tau xy, tau yz, and tau zx. Although now you can use the index notation also, the tensorial notation you can write epsilon I and sigma I is 6 components here what we have written, so that way also you can write. Now if you in general, in the finite element approximation, we have in a finite element approximation, we have these quantities. No, UVW can be written in terms of the interpolation matrix. So that would be H, and depending on what is the element we are choosing, by now you should be able to write the interpolation function and the corresponding. So this is the the displacement. Its variation delta of UVW will be equal to H is no is a known interpolation function. So delta goes with d, the unknown vector of elemental degrees of freedom. And then if you look at the epsilon, so we know epsilon is given in terms of strain displacement matrix B into dE, and then delta of epsilon will be equal to B into delta of dE. So yeah, this is we have UVW, delta UVW, epsilon, delta epsilon. So now we can make use of these, and let us look at the principle of virtual work now. So if you substitute these approximations in the principle of virtual work, you will be able to write that principle of virtual work as integration over volume, and then delta of epsilon is B into delta D. So delta epsilon transpose would be delta D transpose into B transpose. So we will have delta of D transpose into B transpose into sigma dV, and this term is coming from the principle of the virtual work of internal stresses minus the virtual work of external forces. So integration over volume, delta of U transpose, so that will give you delta of dE transpose into H transpose into FB, and then dV, minus we will have the surface forces. So integration over surface, delta of D transpose into H transpose into vector of surface forces ds is equal to 0. So this is what we can write this virtual work, and now we know this equation has to be 0 whatever we have got for arbitrary virtual displacement. So here this should be true for arbitrary delta d. So for this equation to be true, now we get, no, we take out delta d common, and then the coefficient of delta d in the entire expression must be equal to 0. So that gives you this no basic element table governing equation, which is B transpose into sigma dV minus integration over volume H transpose into FB dV minus integration over surface H transpose into T ds, and this will be equal to a null vector. So this is, the element level governing equation. As you see now, we get the element level governing equation. So let us say this is the equation, and this is the element level governing equation. And of course, B and H will depend on what kind of problem you an element you are taking. So depending on that, your B and H would be defined based on the choice of the element. So this is the element level governing equation, which is nonlinear. Governing equation, and it is nonlinear. Why it is nonlinear? Because if you look at this term, sigma is nonlinearly related to strain. So the nonlinearity is coming from here. If it was a linear elasticity problem, sigma would be linear function of strain. So then it would become a linear problem. But sigma is in elastoplasticity, sigma is a nonlinear function of strain, and that is where the nonlinearity is coming. And once if we have a nonlinear equation, so how do we solve this nonlinear equation? So typically we use what is known as Newton-Raphson method. So to solve this equation, to solve equation 1, Newton-Raphson method is used. And how do we, so I think although most of you would have done this Newton-Raphson method, but just a brief, briefly I will, in a two variable problem, let me explain you, and then I will extend it to this problem what we are discussing. So now let me first take an example on Newton-Raphson method, although most of you would have actually done it. So let us say we have two equations, so two simultaneous equation, f1 xy equal to 0, and these are the algebraic equations. So as you know, in the finite element, finally the differential equation is converted into algebraic equation. So this is a nonlinear algebraic equation, set of nonlinear algebraic equations for the element. So let us say we have a example problem where there are two equations, f1 xy equal to 0 and f2 xy equal to 0, and the initial guess for, and we want to solve for x and y. So the initial guess, we need an initial guess here. So let us say the initial guess is x naught and y naught. So what we do is, we as this is an iterative method, so we will perform a number of iterations. So let us say we want to do the ith iteration. So for that, how do we write these equations? So for ith iteration, so we using Taylor series and retaining only the constant term and the first order term in the Taylor series, we can write the first equation as f1 evaluated at the previous iteration, so that is x at I minus 1, y at evaluate y at I minus 1, plus del f1 by del x, and that is evaluated at x I minus 1, y I minus 1 into delta xi, the increment in x for the ith iteration, plus del f1 by del y, and this is again evaluated at x I minus 1, y I minus 1 into delta yi equal to 0. It's actually approximately equal to 0, but I am writing just equal to 0. So this is the first equation using Taylor series and retaining the first term and the second set of terms. We are writing this equation, this f1 xy equal to 0, like this. Now expansion is about xi minus 1, yi minus 1. And similarly, the second equation f2 is evaluated at xi minus 1 minus 1 plus minus 1 into delta xi plus del f2 by del y evaluated at xi minus 1 y I minus 1 delta yi equal to 0. So now if you combine these equations together, so now you can write this set as f1 f2 evaluated at xi minus 1 yi minus 1 plus the gradient matrix, so del f1 by del x, del f1 by del y, del f2 by del x, del f2 by del y, and then into you have, so yeah, let me first write that this is evaluated at x I minus 1 y I minus 1, and then into you have delta x delta y for the ith iteration. This is equal to a null vector. So now what you do is, now in this equation, see, when we are carrying out the ith iteration, the functions are evaluated at the previous values of x and y, and similarly this gradient matrix is evaluated at the previous values of x and y, and into this delta x and delta y for the ith iteration equal to 0. So you can take this term to the right hand side and take the inverse of this gradient matrix, or it is also known as Jacobian of these equations. No, not the Jacobian matrix we discussed in the isoparametric formulation, but Jacobian of this system, and take the inverse of this, and then you can get delta x and delta y. So what you can do is solve for delta x delta y for the ith iteration and update the solution as, so what you will do is that xy for the ith iterations would be xy in the previous iteration, that is I minus 1th iteration, plus delta x delta y calculated for the ith iteration. So that is how no you solve the no use the Newton-Raphson method. So actually what you will do, that you have an initial guess, say x naught and y naught. So first you will solve for delta x1 and delta y1, and then get x1 and y1. Then using x1 and y1, then you will get delta x2 and delta y2, and then update get x2 y2. Then once you have got x2 y2, again then calculate delta x3 delta y3 and get x3 y3. So like that you will continue the iteration. Still no delta x and delta y are no less than a certain value which we call as a tolerance. So that is how no you solve the nonlinear set of nonlinear set of algebraic equations using Newton-Raphson method. So now this equation 1 what we have written here, this equation is a nonlinear equation, so we want to solve this. So we do the same thing, that is we use the Taylor series expansion. So now let me see that now coming back to the our problem. So expanding equation 1 using Taylor series and retaining only the first no first two terms. So let me first write the gradient term or the Jacobian term, which is the term like this what I have written here. So now we have the first term is B transpose into sigma, and of course for a small deformation B is a known quantity, so that doesn't contain any unknown. So only unknown is with the sigma. Sigma is an unknown, is a no nonlinear function of strains. So that is what we want to take the derivatives. So we will write this equation as integration over volume, and then we will have B transpose, and then now we have six components of sigma: sigma xx, sigma yy, sigma zz, tau xy, yz, and zx. And let us say each is a function of epsilon xx, epsilon yy, epsilon zz. So first we expand now this, take the derivatives of sigma with respect to different strain components. So what you will do is you will take the first is the sigma xx. So the first row will be derivatives of sigma xx. So we will have del sigma xx by del epsilon xx, del sigma xx by del epsilon yy, del sigma xx by del epsilon ZZ, like that with respect to all the six components of strain. Del sigma XX by del gamma XY, del sigma XX by del gamma XY, del sigma XX by del gamma YZ, del sigma XX by del gamma ZX. So like that, no, you will have for various terms. So similarly, the second row would be derivatives of sigma y, del sigma yy by del epsilon xx, del sigma yy by del epsilon yy, and so on. No, so you can write no similarly. So this finally will be a 6 by 6 matrix. Into now you are going to have the increments. So no, the exactly the way we wrote no this no derivatives of all the equations. So like this gradient matrix is there, and then this increment is there. So the increment would be, because we are taking the derivatives with respect to strain, so the increment will be there in the strains. Here the increment term. So of course, if you look at this whole thing, now this whole thing is evaluated at previous iteration, that is at I minus 1th iteration, and as you see, this is a 6 by 6 matrix, and this is multiplied with delta epsilon xx, delta epsilon yy, delta epsilon zz, delta gamma xy, delta gamma yz, delta gamma zx, and this is evaluate this will be for the ith iteration, this value. And as you see, this is a 6 by 1 vector. And then the integration, that is there are no dv there, integration is there, so dv term has to be there. Then now we write the first term what I have written here in these equations. So that is basically no, then I have written first this term, then let us say this term. So this term is simply integration over volume, and then we have B transpose into sigma, and this whole thing is evaluated at previous iteration. So at I by minus 1th iteration is into dV. And then of course the because we are assuming that the body forces and surface attraction forces are independent of deformation, so these remain same, although in solving actual problem we will divide the total load into a number of load steps. So then these Newton-Raphson iterations you will do for each load step. So that is how you will be actually doing this. So we will have now this load term, so integration over volume, we have H transpose into FBdV minus integration over surface H transpose into TdS, and this is equal to a null vector. Now what we can actually do is now write this equation in the symbolic form. So the first term, that is this term I am going to write in a symbolic form, so the integration over volume, and then we have B transpose, and this whole 6 by 6 matrix, this matrix, let me write it as derivative of another stress with respect to strain, so del sigma by del epsilon, and this whole thing is evaluated at I minus 1th iteration, then into delta of epsilon, which is calculated for the ith iteration, into volume integral, and then plus of course this term, these terms go as it is, integration over volume B transpose into sigma evaluated at I minus 1th iteration into dV, and minus the body forces and surface forces terms. So H transpose into FBdV minus integration over surface H transpose into TdS is equal to a null vector. So this is what you get this as the equation. Now let's look at finally, because our unknowns in finite element approximation are the nodal degrees of freedom. So the ultimately for the element, the vector of elemental degrees of freedom. So let us say this is equation 2, and we already know that epsilon is already B into dE, strain displacement matrix into vector of elemental degrees of freedom. And similarly, so if you look at the delta of epsilon, the increment in the strain vector can be written as no b, because b is no shape functions, the derivatives of the shape function which is no into delta of dE. So we will know the delta epsilon can be written in terms of increment in the elemental degrees of freedom, so delta of dE. And let us also say that this del epsilon by del sigma, del epsilon, no, del sigma by del epsilon, sorry, the del sigma by del epsilon, which is a 6 by 6 matrix, is written as a tangent constitutive matrix, so CT, which is a 6 by 6 matrix, and this is known as tangent constitutive matrix. So yeah, so these are the relations we can make use and substitute in the equation 2. That's what I'm going to do. So if you look at the, of course, delta
Sir,
sigma here. Yeah, yes,
One
please.
doubt, sir.
Yeah,
We are putting the value of xi minus one, basically epsilon I minus one in case of B transpose also, right?
yeah, b, of course, b is actually, in this small deformation problem, b is known quantity. So although I am putting over the entire this thing b transpose into del sigma by del epsilon I minus 1, but b is known, so it doesn't depend on the unknowns. So it will be ultimately this del sigma by del epsilon, which will be evaluated at previous iteration.
Okay, sir.
Yeah, and similarly here also sigma is the term which would be evaluated at previous iteration, and then this term would be computed.
Okay, sir.
sir,
Yeah.
are we considering only two terms?
Yeah, please repeat again, be little louder.
Sir, are we considering only two terms?
Two terms in the sense.
Sir, for Taylor series expansion.
Yeah, for Taylor series we are considering first two terms. That is how we can easily solve the problem. So if you are looking, no, if you look at this example I have taken, so in this I have taken the two terms in the Taylor series expansion: the value of the function at the previous iteration and the first gradient of the function. So that is these terms, and same thing we are doing with the this element level governing equation problem. So we are doing just two terms, yes. So we that's how now finally the you will get the linear, the linear equations in the incremental displacement. So these can be solved easily. So that is why we are considering just two terms. So now if you look at this equation 2, so I can say now that equation 2 can be written as, with this approximation what I said, epsilon is b into d and delta epsilon is b into delta d. So we can now see this equation we can write as the integration over volume 1 b transpose b already have, and then d sigma del sigma by del epsilon is ct, so 6 by 6 matrix, and then we have delta epsilon. Delta epsilon is again b into delta d, and delta d can be taken out of the integration because that's the increment in the elemental degree of freedom at the node point, so they're independent of the integration variable. So we can write this as b, and then the integration over the entire volume, and this is what is known as a tangent stiffness matrix. This is evaluated at previous iteration, and then into delta of de evaluated for the current iteration, that is ith iteration, and this will be equal to all other terms you take to the right hand side. So the first term would be minus integration over volume b transpose into sigma dv, and this is evaluated at previous iteration, that is I minus 1, and plus you have these body and surface forces, so h transpose into fb dv plus integration over surface h transpose into t ds. So this is the finally equation what you get over here, and now in this particular
Sir,
quantity, yeah, yes.
sir, we take the uh, B matrix at ith iteration into the I minus one iteration because of the small deformation term.
Yeah, actually, see, if you look at B is going to be for small deformation problems. B is going to be independent of DE. Ultimately, your unknowns are the vector of elemental degrees of freedom. So B will be for if you are considering finite deformations with the nonlinear terms in the strain displacement relations. In that case, B will also be function of D. But for the problem I just said, B is going to be independent of D. So ultimately, you would be evaluating this CT at the previous iteration, that is at I minus 1 iteration, and then you will be constructing this matrix.
So B is
Similarly,
same
here
over
in
the
the
all
stuff,
the iteration.
yeah, B will be same for all the iterations. Similarly, here B will be same, only sigma will be changing from iteration to iteration. And this term is, the integration over volume B transpose CT into B dV is known as tangent stiffness matrix. Because no, this is relating giving the no relationship for the incremental displacement. So this is coming from the increments, and this is known as tangent. So in the corresponding uniaxial problem, it is equivalent to no considering a tangent and then moving along that tangent, satisfying the equilibrium equation, that is the equation 1 which we wrote. So now, so this is the finally the element level governing equation. So you will, for each element you have to do this, then assemble it, impose the boundary conditions, and then solve this for the incremental displacement. And once you get the incremental displacement, calculate the incremental strain, and then go for the next iteration. So that is how you will be solving. Although the detailed, the total set of steps I will be talking about later. But first, let me, when we are solving an elasto small deformation elastoplasticity problem, so let me also explain you what are the concepts involved in the small deformation elastoplastic analysis. So a small no concepts involved. So main things I am going to just briefly tell you about that. Concepts involved in small deformation elastoplastic analysis. So now in each step what we do, once we calculate the incremental displacement for the system as a whole, and then of course you can get for the element incremental displacement delta D, and from once you have delta D you can get the incremental strain. So first step in this plasticity analysis is incremental strain is additively decomposed into elastic and plastic parts. If you are considering finite deformation, then you would be using the multiplicative decomposition. So since I am talking about a small deformation gradient problem, so we are using additive decomposition. So first step is incremental. First is the concept involved is that incremental strain, let us say I am denoting the incremental strain by actually D. You can also use delta. So D of epsilon is additively decomposed into elastic and plastic parts. Elastic and plastic parts. So what you do here, what I mean is that when you get the incremental strain, so you have this D of epsilon, and this has two parts. One is the elastic part of the strain, like in the first I drew the uniaxial stress strain diagram. So I had demonstrated you what is the elastic strain and what is the plastic strain. So similarly, the incremental strain is also additively decomposed into elastic part of the strain and the plastic part of the strain. So D of epsilon P. So superscript E is for elastic here, although I have also used the E for element, but here no, the in the strain superscript E is for elastic and superscript P is for plastic. So that you should keep in mind. So here this is, now if you look at, this is the total strain increment. This is the elastic strain increment, and this is plastic strain increment. So now for the if you look at the uniaxial case, again let me demonstrate the incremental part. So uniaxial case, so that means the kind of material characterization you do using uniaxial test, so that kind of a situation. So let us say we have the stress strain curve, so that is sigma xx here and epsilon xx, and the stress strain curve is a initially linear elastic, and then elastoplastic. So yeah, this slope is E, and now see, this is the initial yield stress. I have already told you this is sigma capital Y is for yield and naught is for initial, so this is sigma Y naught, and the slope of the curve is Young's modulus E. Now if you are know somewhere talking about the incremental strain, so let us say we are here in the this is at I minus 1, and this is where we are going to ith iteration. So in this, the total increment, if you look at in the increment in the strain, so this is d of, let us say, epsilon xx, the total increment in the strain. This is the total increment in the strain. If you look at the increment in the stress, so if you look at this is going to be the increment in the stress, so this would be d of sigma xx. Now if you want to identify what is the elastic part of the increment and the what is incremental strain and the plastic part of the incremental strain, so kind of we consider unloading from this point by a amount of stress going down by d sigma xx. So we just come up to here, so this is the unloading path. So this is the unloading, the slope of this curve is going to be. So now from here to whatever you are getting, this is the permanent strain d of epsilon xx p, and the remaining part, this part, is d of epsilon xx e. So this is what we are talking about. And see, now if you look at d sigma xx, so now the d sigma xx can be written in terms of Young's modulus E into d of epsilon xx elastic. So the same constitute, the Young's modulus can be used to relate d sigma xx with the d epsilon xxe. And you know that d epsilon xxe can be written as d of epsilon xx minus d of epsilon xx p. So we can write this relationship in this manner. So for the uniaxial case, this is how you can write. Similarly, for the multi-axial case, you can actually write the increment in the sigma. This is the infinitesimally small increment. Differential increment in sigma is equal to elastic constitutive matrix Ce into d of epsilon e, or you can say that d of sigma. Yeah,
Sir, here are we assuming that unloading is happening with a slope which is equal to E?
yeah. Though that is what is the observation from the experiments, that nearly this unloading happens at the same slope which is there during elastic part of the loading.
Okay.
Yeah. So slope of this curve here, if you look at this slope, that is equal to E. So now this can be d of epsilon E can be written as d of total strain increment minus the plastic part of the strain increment. So we are ultimately writing the differential increase, the increment in stress in terms of differential increase in incremental strain and differential incremental plastic strain. So if you look at here again, this would be elastic constitutive matrix. This is elastic constitutive matrix. So that's the first thing. No, in the in a small deformation elastoplasticity, we decompose the total strain into elastic part and the plastic part, and then write the increment in the stress in terms of elastic constitutive matrix and the elastic part of the strain increment. So that's one thing. That is one thing which is needed. This is the one concept which is needed. Then the second thing you need in the elastoplasticity is yield criteria. So yield criteria, or we also call that simply as yield function. So now, of course, the yielding is onset of yielding happens at the sigma y naught in uniaxial loading. But when we are talking of a multi-axial situation where all the components of stresses are, let's say, non-zero, then we have a function f which is known as the yield function, and this is a function of your stress tensor, the plastic work of stresses WP, and the back stress, which is the denoting the translation of the yield surface. So I will explain, of course, that also. So if you look at this, sigma is 6 by 1, this is scalar, WP is scalar, and this is also 6 by 1, this will equal to 0. So this will be the form of your yield function. Out of this, the sigma you already know, WP is the WP is a scalar, and it is plastic work of stresses. That is work done by stresses under plastic deformation. So plastic work of stresses, and this no alpha is known as back stress. Although in the literature you can find different notation. Sometimes you will find alpha is denoted by x, and why we need this alpha is actually for the if what you need this alpha in the hardening to describe the kinematic hardening. So this back, the back stress tensor alpha is used for representing kinematic hardening. And kinematic hardening is the result of what we call, in the literature as the Bossinger effect. So now I need to explain you what are these there are two types of hardening. Of course, you can always have a mixed hardening, so which is combination of these two basic types I'm going to discuss. So since this hardening term has come over here, and see, if you look at, this AF could be, if you use one Mises yield criterion, then it would be, the expression of F would be in terms of the form, it would be in the form of one Mises stress. If you are using Tresca criterion, then F would be in the form of Tresca criteria. So there are different criteria. It's according to the problem you are handling, you have to decide what yield function you want to use. Then, since I am talking about the hardening, so let me first introduce you this what is known as isotropic hardening. So in the essentially what it means is that when you actually, let us say, let me talk about the stress strain diagram. So we have now again sigma xx, we have epsilon xx, and now if you load the material, so initial elastic portion is there, and this stress is sigma y naught, initial yield stress, and then there is a elastoplastic deformation, and so you go, let us say, up to point A. And now there are two things. If you unload this, unloading would be, this is slope of this graph is E, the slope of this will also be E. And if you reload, so the subsequent yielding will start only at the stress corresponding to point A. Now it will not start somewhere at no sigma y naught. So the yielding will not start something like this over here, but yielding will start at point A. But if we do the unloading and then go in the compressive side, that it be compress the same specimen. Should be come like this. This is a straight line, and go here. So in the compression you will find that the yielding is going to take place at a stress which is in magnitude is equal to sigma xx at A. So let us say we have in the plastic deformation we have gone up to point A and the corresponding stress is sigma xx at A. So this yielding in isotropic hardening, if the material is depicting isotropic hardening, so the magnitude of this stress is going to be sigma xx A. So the yielding will take place at that stress level. So this is known as isotropic hardening. So in the same, if you unload and reload, the yielding will start at this point A. It will not happen at this point. And if you are unloading and then going into the compression, the yielding in compression will take place at a stress level which is same in magnitude, equal to stress at point A. That is sigma xx at A. So this is known as isotropic hardening. So this is again, we get this information from experiments. Now if you have the biaxial state of stress, and if I represent the yield function as, let's say, using the one Mises yield criterion, so you have, say, principal stress sigma 1 and principal stress sigma 2 space. So the initial yield surface would be something like this. It would be an ellipse like this, and then subsequently when we have the material has undergone elastoplastic deformation, so the subsequent yielding will take place at a higher stress. So here if you see, this is the initial yield surface and this is the expanded yield surface. We call it as in the isotropic hardening there is a expansion of the yield surface. So this is expanded yield surface, and this is expansion is what is attributed to isotropic hardening. Now so this is a bit explanation on the isotropic hardening. I know if you have any doubts and questions you can ask if you don't understand any of these concepts. And then there is a kinematic hardening. So let me also introduce this kinematic hardening briefly.
Sir, is this curve for one Mises criteria?
Yeah, right. This
Okay.
right hand side what I have plotted is for the one Mises. If you are using one Mises yield criterion, then your yield function is going to be a actually ellipse, and in the sigma 1 sigma 2 space it would be just a ellipse. So this is also ellipse, although my sketch is not very good. This is also ellipse, and this is the initial yield surface and this is the expanded yield surface after, let's say, going to point A. So now you can see equivalently that yield stress of the material has due to strain hardening. So this this is actually due to strain hardening. And if you go into the material science, so it's kind of basically the accumulation of defects at the grain boundaries. So next is the kinematic hardening, and in this the yield surface actually translates in the if you see in the isotropic hardening, the yield surface is expanding, and in the kinematic hardening the yield surface actually translates. Yield surface translates. So now let me demonstrate again through the uniaxial and the biaxial state of stress. So what it means is, now if I look at the uniaxial stress strain diagram, so you have sigma xx and epsilon xx, and then you have this elastic loading, then elastoplastic loading. This is the initial stress sigma y naught, and then you are loading going up to, say, point A. When you do unloading, so now when you unload and go into the compression, so in the compression zone the yielding will start at a stress such a way that this is 2 sigma y naught. So because now the stress at point A is higher than sigma y naught, so the yielding will take place at a magnitude of stress which is smaller than sigma y naught in compression. So this is known as kinematic hardening. So in the isotropic hardening, this would get extended and go something like this. And this no in that case, if you look at this magnitude, I have already explained to you that this would be sigma xx, my magnitude would be equal to sigma xx at a. So this is kinematic hardening, and this is what is your isotropic hardening. So if no the material has already yielded in tension, then the yielding in compression would take place at a lower stress, so that compared to the initial yield stress of the material. So that means this is going to be, this magnitude is going to be smaller than sigma y naught. So that is what is known as the kinematic hardening, and this is observed in most of the metals. If you express the same thing in the for the biaxial state of stress in terms of principal stresses sigma 1 and sigma 2, so you will have initial this is the initial yield surface, and now once the material has been loaded in tension, so then this yield surface will translate and will become like this. So this is the initial yield surface, and this is the subsequent yield surface. Subsequent yield surface. So if you know, because the material is initially loaded in tension, so now we will see in the compression, the stress is smaller, and if you both sigma 1 and sigma 2 are positive, so now for subsequent yielding, the stress has to cross this limit, so which is higher than what it was initially there. It is higher than sigma y naught. So this is known as actually basically the kinematic hardening. So no, I have talked about this hardening. So actually, that although since when I talked about yield stress, so there was a concept of alpha, and alpha was denoting the kinematic hardening. So I explained you the isotropic hardening and kinematic hardening. But the third concept which is needed in the elastoplasticity is the strain hardening. What is the strain hardening law of the material? What kind of strain hardening is there in the material, whether it is isotropic hardening or is it kinematic hardening or it is mixed hardening. You can have the combination of these two, that is known as mixed hardening. Then the another important thing, yeah, I think just let me take few more minutes so that I complete this. So the other, no, the fourth thing, important concept, because when I wrote the incremental stress, I wrote the incremental stress in terms of incremental strain and incremental plastic strain. So we need that, and that's an additional unknown. So we need a law to calculate the plastic strain. So that law is referred to as what is known as flow rule. Why flow? Because plastic deformation is like flow of the material. So it is, that is why this is known as flow rule, and this is required to calculate plastic strain increment. This is required to calculate plastic strain increment. And let me write that. So sometimes it is also referred to as normality rule. So d of the incremental plastic strain, which is a 6/1 vector for a general case, would be some multiplier lambda times gradient of a scalar function q. So gradient with respect to sigma, so del q by del sigma. So here this lambda is known as plastic multiplier, and this q is a scalar plastic flow potential function. Scalar plastic flow potential, this is known as potential, like Now if you would have studied fluid mechanics, so there is a potential function, velocity vector can be written as gradient of potential function. So similarly here, this plastic strain is written as gradient of, that is derivative of q with respect to components of sigma. So it is known as flow potential. This scalar plastic flow potential function. And there are, in the literature of elastoplasticity, if you see, there are two types of flow rules. One is known as associate associative flow rule. So in this associative flow rule, the plastic potential function q is taken same as yield function f. We have used annotation f for yield function. And so you can say here that the plastic flow potential function is taken same as yield function. Plastic flow potential. So these are the concepts which you need to understand, to solve plasticity problems. It's taken same as yield function. And there is another one known as, so most of the metals of course follow this associative flow rule, but none no, say for example the concrete and all cement and also soil etc., they mostly follow non-associative flow rule. So in this you will have to choose some other function as the plastic potential function. It will not be same as yield function. So that is, the plastic flow potential function is different from yield function. In the non-associative flow rule, non-associative flow plasticity, you use you say that the plastic flow potential function is different from yield function. So yeah, so this is about the flow rule, and the last thing in concept you need to understand is the unloading criteria. So I already said the unloading happens parallel to the initial loading elastic region. So unloading criteria I have already talked about in the diagrams, but you need to understand that what is the unloading criteria for the material. So that's the last thing which you need to understand. So I think this is where I want to stop. I will continue subsequently. We will continue discussing the elastoplasticity problems subsequently. So I want to stop here. Now if you have any questions and doubts, you can ask. Yeah.
Sir, in material science, actually, we were taught something like sigma equal to k into epsilon dot to the power m. So,
Yeah,
is the kinematic hardening the
that
same?
is isotropic hardening. That is isotropic hardening.
Okay, sir. So, but it was differential of epsilon in the fall.
So it could be it is not necessary actually. It can be differential of this, it can be function of actually, if you look at the yield stress can be in isotropic hardening. Yield stress could be function of plastic strain itself, nonlinear function, either linear or nonlinear function of plastic strain. And it could be also for where the dynamic problems are there, rate dependent plasticity. So the yield stress could also be function of a rate of plastic strain. So both could be there. So sigma y could be function of epsilon p and epsilon p dot. But
Okay,
here
sir.
we are talking about rate independent plasticity. So I said of course I have just said that yield yield stress is a function of plastic strain. So yield stress changes with subsequent elastoplastic deformation.
Okay, sir.
Yeah. So are there any other questions? Anybody? Yes, anybody? Any other question?
Sir, for this portion, which book should we refer? Jane Reddy?
Yeah, generally has some part of it. Yeah, but you will have to, for plasticity actually, you need to refer some book on plasticity. So generally the nonlinear one has some part, but may not be the entire thing. But I have taken these concepts, so I know what I have. Finitely one formulation is of course the standard way we formulate any nonlinear problem, and then the concepts of plasticity you have to read from a plasticity book.
Okay, sir.
Yeah, I think that
Sir,
name of the book I don't remember. Yes,
sir, after next week, minor will be there.
yeah.
So, like, what will be the syllabus for that?
Syllabus will be whatever we covered till say 18th. I think yeah 17th, because 19th is the 19th is the exam. 11 a.m. is the end of the exam, so I will set it. Let us say some 9:30 or something like that. So 9:30 to, yeah, 9 or 9. So I will set 9 to 10:30, something like that, on Sunday 19th. So the syllabus would be whatever we covered till 17th of September.
Okay, and sir, the kind of questions which will be asked, will they be numerical or will they be like derivation type of?
There could be few derivations and conceptual questions, and there can be some numericals, so simple numericals.
Okay, sir.
Although, as you see, asking a full-fledged numerical questions is difficult, to do in the limited time. So most of what we are discussing here needs to be done using a computer code. So
Okay.
that is why I will have to set the question such a way that it is doable in that 1.5 hours. So there would be some derivations, there would be some conceptual questions, and there would be some smaller numericals.
Okay.
Are there any other question, anybody? Hello? Okay, so if there are no questions, I'm stopping here. Thank you all for your attention.
Thank you, sir.
Thank you, sir.
Okay, welcome.